Bored of your oscillator's same old basic waveforms? Why not morph them into something more exciting? Here's a super simple double wavefolder that will add a ton of tonal complexity to your patches. Before we can start designing our circuit, we'll first need to make sure we understand what wavefolding actually is. Thankfully, that term is pretty hard to misinterpret. A wavefolder quite literally takes a waveform and folds it in on itself. Here's what that would look like with a triangle wave as the input signal. As you can see, everything above this threshold is folded inward, so that the tip of the triangle now points down. In practice, this would create a bunch of additional overtones that give the resulting output an almost metallic feel. Of course, not all types of waveforms are equally suited as an input signal here. You won't gain anything by folding a square wave, for example. On the contrary, you'll just lose a bit of volume. Try it with a sawtooth wave though, and you'll notice that if you set the folding threshold just right, the result is actually a perfect triangle wave. Okay, but how do we make this happen? The circuit will probably be quite complex, right? Yeah, not really. All we need are three components: two same-value resistors and an NPN transistor. If we set them up like this and send an oscillation into the transistor's base, we can pick up a folded version at the collector. Now, if you've worked with NPN transistors before, you might say, hold on, how is this a wavefolder? It's just a box standard amplifier. And you would be right. What's worse, it doesn't really amplify anything since it has a gain of -1. So all it does is invert the input signal while keeping the volume the same. Then why do I call this a wavefolder? Because it is if you abuse it. To understand why and how, let's dissect this circuit step by step. Functionally, we can split it into two sections: the resistor up top and the transistor and resistor below. Let's start with the lower section. These two components in conjunction serve one simple purpose. They're meant to convert voltage into current. More precisely, the voltage we apply to the base into a current flowing through transistor and resistor. Okay, but what is the relation between those two variables? Well, for the transistor on its own, the relation between base voltage and collector current is exponential. Conversely, for the resistor, the relation between the voltage across it and the current flowing through it is strictly linear. So when the components are paired up, we can see that their behaviors are clashing. While the transistor wants to ramp up its current throughput exponentially, the resistor only allows for a linear increase. This means that the resistor is the bottleneck in this system. It throttles the transistor. So for a given base voltage, the current flowing through transistor and resistor will be almost the same as the current flowing through just the resistor with the base voltage applied across it. I say almost because activating the transistor eats up a small but fixed amount of current. So it will always be a little bit lower. Now let's look at the upper part of our amplifier/wavefolder, which is just a single resistor connected to the positive rail. That resistor serves the exact opposite purpose: convert current into voltage. It works like this. The more current we pull through the resistor, the more the voltage below it will drop. If we put this together with the lower half now, it should become clear why the voltage at the collector almost mirrors the voltage at the base. Because for every volt added to the base voltage, we push an additional 50 microamps through the bottom resistor, which in turn means that we have to pull that current through the top resistor. And because that resistor is of the same value as the one at the bottom, the voltage below it will drop by exactly 1 volt. There are 2 caveats here though. First, the absolute collector voltage will be a small but fixed amount higher than the base voltage. This is because, as we said earlier, the transistor eats up a bit of current while active. But second, and more importantly, this mechanism only works as long as the transistor can pull enough current into its collector. Let's look at this using a quick graph. Well, imagine we steadily increase the base voltage from minus 12 volts all the way up to plus 12 volts. In the region between minus 12 volts and around 450 millivolts, everything works as expected. The collector voltage drops in sync with the base voltage. But after the base and collector voltages meet, something strange happens. The collector voltage starts rising again. What's up with that? Well, we've run into a phenomenon called transistor saturation. This happens when we try to pull more current into the collector than is available. Think of it like this. If we'd remove the transistor from our circuit, we'd see 600 microamps flow through both resistors. And we can't increase that current without bumping the voltage or reducing the resistance. So as we push the base voltage above the 450 millivolts line, the transistor tries to blow past that 600 microamps current limit. But since it can't get more current out of the top resistor, it will switch to an alternate strategy. And that strategy is pulling large amounts of current into the base, which will not only cover the missing amount, but also increasingly substitute the current flowing into the collector. As a result, less current is pulled through the top resistor, and the voltage below it starts to rise. More precisely, for every volt added at the base, the collector voltage will increase by the same amount. This means that we have 2 distinct regions in our graph. One where the collector voltage is roughly the inverse of the base voltage, and one where it's roughly the same. So if we'd send a triangle wave oscillation into the transistor's base, every part of the wave that crosses this 450 millivolts threshold will be folded over in the output. Great! To make sure this actually works, let's set it up on the breadboard. Thankfully, doing that is super easy. Plug in a generic NPN transistor and connect the collector and emitter to the positive and negative supply rails through 20k resistors. That's it. If I now send a triangle wave into the base while monitoring the voltage at the collector, we should see some folding happening. And yeah, it works. Since I've routed my triangle wave through a mixer before sending it into the circuit, we can play with its volume to check the effect this has. As you can see, more volume means more noticeable folding, simply because a bigger part of the triangle is passing the folding threshold. And here's what this looks like with a sawtooth wave. At maximum volume, we almost fold it into a triangle, though we'd have to fix the offset to align it with the folding threshold properly. So far, so good. But the problem with our design is that it only affects the bottom of the output waveform. In a traditional wavefolder, you'd want to fold both the bottom and the top though. To get there, we'll first check out an alternate version of our circuit that folds just the top of the output waveform. As you can see, the only real difference here is the type of transistor we're using. I've simply replaced the NPN with a PNP transistor. And since the PNP transistor is basically just the NPN transistor's bizarro twin brother, everything about it is inverted. Collector and emitter switch positions, and the current flowing through them increases as the base voltage decreases. So if we look at the relation between base and collector voltage for this circuit with another graph, we can see that the 2 regions are switched. In the space between plus 12 volts and minus 450 millivolts, the collector voltage rises as the base voltage drops. And once they meet, they both start dropping together. So if we use our triangle wave as an input here, we should get an output with a folded top. To try this, I'll swap the NPN for a PNP transistor. And yeah, that works as expected. Great. Now the question is, how do we combine these two folding circuits into one? Lucky for us, it's actually pretty straightforward. All we have to do is wire them together like shown here. Base connects to base and collector connects to collector. If we then send in our triangle wave on the left, we can pick up a top and bottom folded output right here. It works like this. At 0 volts base voltage, without a connection between the collectors, the NPN's collector would sit at plus, while the PNP's would sit at minus 700 millivolts. Wire them together and we get 0 volts, since the two voltages cancel each other out. Now, if we increase the base voltage, the NPN transistor will open up, while the PNP closes down, leaving us with a current deficit at the collectors. This forces us to pull more current from the positive rail through this resistor, which in turn will cause the voltage at the collectors to drop, at least until we run into the NPN's folding threshold. Because then that NPN goes into saturation and the collector voltage starts climbing up again. And the same idea applies in reverse if we decrease the base voltage from the 0 volts line. The NPN will close down while the PNP opens up. So we pull less current through the resistor and the voltage rises. Until we hit the PNP's folding threshold, it goes into saturation and the collector voltage starts dropping again. So we get two folding thresholds, one slightly above and one slightly below the 0 volts line. To test this, I'll set up a separate NPN folder over here. Then I'll connect both transistors' bases and collectors. And here's what the output looks like. As expected, both the top and bottom of our triangle get folded over. Perfect. So how do we listen to this now? Unfortunately, we can't just attach an output socket to the transistor's collectors, since that would mess with the core mechanism by pulling more current through it. Okay, so we'll simply route the collector voltage through a non-inverting op-amp buffer connected to an output socket, right? While that would work, there's an alternate approach that helps us streamline our design a bit. To get there, let's first clean up the existing schematic while keeping the circuit itself the same. We'll move the two transistors directly on top of each other. Then we'll pull both collector resistors over to the right. This leaves us with these two vertical paths on and between which current flows. Let's take a closer look at the one on the right. Since this is a 50% voltage divider between plus and minus 12 volts, the central node sits at 0 volts. At least until we start drawing current from it. Then the voltage will drop by 100 millivolts for every additional 10 microamps we pull through the top resistor. Interestingly, we can get exactly the same behavior from a single 10K resistor to ground. If we don't pull current through it, the voltage on the other side is 0 volts. And if we do, the voltage drops by 100 millivolts for every 10 microamps we pull. Great. So we could simply replace the two 20Ks with a single 10K to ground and save ourselves a resistor. But we can take the optimization even further. We'll use an inverting buffer to buffer the collector voltage instead of a non-inverting one. This has two benefits. First, we undo the inversion that the wavefolding stage applies to the input signal. So the output will be in phase with the input again. And second, the new 10K resistor gets to work double duty. It's providing the extra current for our two transistors, and it's playing its role as input resistor for the inverting buffer. This works because in an inverting buffer, the op-amp's inverting input is what we call a virtual ground node. It behaves just like a path to ground without actually being one. So connecting the collectors to the op-amp's inverting input through a 10K is functionally the same as connecting them straight to ground here. Great, so let's see if all of that works as expected. First, I'll rearrange our transistors and get rid of the two 20K collector resistors. Then I'll set up a TL074 and configure one of its op-amps as our inverting buffer using two 10K resistors. Place a 1K resistor for short circuit protection after the buffer's output, and we're done. And here's what the result sounds like. By adjusting the input volume, we can again change the effect's intensity. Note how if I push it up all the way, the output crosses the folding thresholds a second time, but doesn't get folded. That's because we're just going deeper and deeper into saturation of the same transistor. Great, but because relying on an external mixer to adjust the effect's intensity feels pretty clunky, we should come up with an integrated solution. For that, we'll set up a simple input volume attenuator. Instead of using a single potentiometer as a variable voltage divider, we'll go with this slightly more elaborate solution though. And that's because it makes sense to restrict the input volume's range somewhat. If the intensity knob is dialed all the way down, you'd expect the input signal to just pass through the circuit unaffected, instead of going completely silent. Also, it would be great if the output volume stayed the same no matter the set intensity. We can achieve this if we make sure that the signal always fits nicely between the two folding thresholds. This means that the minimum input volume should be just shy of crossing the thresholds, while the maximum should be just shy of crossing them a second time. After some trial and error, I settled on a fixed 100K input resistance, followed by a 10K potentiometer and a 4K7 baseline resistance to ground. Given a 10 volts peak-to-peak input, this outputs a range of 0.4 to 1.2 volts peak-to-peak, which fits nicely between the two folding thresholds. Before we can send the result into our wavefolding stage, we'll have to buffer it with an op-amp to avoid loading effects. To try this, I'll first set up the input volume attenuator. Next, buffer the result. Finally, I'll send the buffered output into the wavefolding stage. As you can see, the output volume stays roughly constant as I sweep the intensity knob. Cool, but even at maximum intensity, the output sounds a bit too tame for my taste. So let's fold the folded signal again. For that, we'll simply add another wavefolding stage after the first one's output buffer. Then we'll have to adjust the input attenuator's range. That's because we've previously made sure that the input signal doesn't cross the folding thresholds a second time. But in order for the additional stage to have any effect, it needs to. So we'll simply replace the 10K potentiometer with a 20K. This roughly doubles the attenuator's range, allowing us to boost the signal to the necessary levels. So I'll first set up another wavefolding stage and then hook it up to the previous one. Next, I'll replace the 10K potentiometer with a 20K. And here's what the result looks and sounds like. As you can see, the second stage kicks in right here. Now, if you're like me, you might still look for a bit more zing. In that case, no worries, we can harsh up the output even more. For that, we just have to increase the gain of the first folding stage's output buffer. Because if it's more than 1, the signal will get folded 1 additional time for free. Why is that? Because coming into the second stage, the signal will now wiggle across the threshold 1 additional time before heading off to the other one. In my experiments, increasing the gain by a factor of 2 gave me the best results. So we'll replace the 10K feedback resistor with a 20K. Now, to keep our intensity knob's behavior the same, we'll have to adjust the attenuator's range. Because otherwise, the second stage will fold the signal even at minimum intensity. To avoid that, we'll about halve the baseline resistance in the attenuator. That way, at minimum intensity, the signal is occupying only half the area inside the first stage's folding thresholds. Blow that up by a factor of 2, and the result should fit snugly between the second stage's folding thresholds again. As a final touch, we'll get the circuit's output volume up to the standard 10 volts peak to peak. For that, we just have to bump the second output buffer's gain to 22 by increasing its feedback resistance to 220k. Cool, so let's implement this final adjustment. I'll replace the 10k resistor here with a 20k, the other 10k over here with a 220k, and the 4k7 to ground with a 2k. Thankfully, the signal does pass through unchanged at minimum intensity. Next, let's see what happens as I dial it up. As expected, we get these additional spikes in the output that make it sound even more harsh and metallic. Great. And with that, our double wavefolder is done. As always, if you'd like to support the channel, check out my Patreon page. You can get access to a bunch of bonus content there, like a live stream replay archive, a private Discord community, and early access to my videos. Anyways, thanks for watching, and until next time. See ya!